Hello guys, this is 3.4 curve sketching, and what we're going to learn in this section is we're going to use the idea from 3.3, right? Finding local max, local min, first derivative test, second derivative test. We want to use all the information that we have, try to graph a curve, right? Without using a calculator, right? By just identifying the behavior of the function at any given point, right? So let's go ahead and get started. Let's start with looking at the steps to curve sketching. All right, so we have these 6 main steps. Now we're going to go through each one of them using an example, and then we will talk about the details in each step and what to do there. All right, so let's start by looking at the example. We want to graph y equals x to the fourth power minus 4x cubed plus 10. All right, and let's start with step 1. All right, step 1 says we want to find the domain. Now that's a polynomial, right? So the domain would just be all real numbers, right? Negative infinity to positive infinity. Now, do we have any symmetry? We can check using even or odd function, but in this case, we can see that the exponent, we have both even and odd powers. So they are neither even or odd. That means that they're not going to have any symmetries. And the equation y being a polynomial, it's not going to have any asymptotes, right? So this is one of the nicer type of function that we can look at because it's a polynomial, right? And has no symmetries and no asymptotes as well. Okay, and that's step 1. Very straightforward, right? Okay, step 2. We want to find the derivatives, y prime and y double prime. We want to find the first derivative and second derivative. All right, so y prime, let's take the derivative, right? Just simple power rule, bring down the power, decrease the power by 1. Bring down the power, 4 times 3, decrease the power by 1. And the derivative of a constant is 0. And we're done, right? That's the first derivative. And let's repeat that again by taking the derivative of y prime to get y double prime, which is the second derivative of y. And we do the same thing, bring down the power, 3 times 4, that's 12, x squared, minus, bring down the power, 24 times x. All right, and that's the second step, right? Finding y prime and y double prime, and that's it, right? That's it for the second step. Next, let's look at the third step. All right, now step 3, it says find the critical points of f. Let's start with that first, right? So critical points or critical numbers, right? We want to let y prime be equal to 0, right? So we have 4x to the third power minus 12x squared is equal to 0. And let's try to solve this, right? We can factor out 4x squared and we'll get x minus 3 is equal to 0. And from this equation, we can see that my critical numbers or critical points are x equal to 0 and 3, right? So those are my critical numbers. And if you look at the second part of step 3, it says find where the curve is increasing or and decreasing, identify the function's behavior at the critical points, right? So this is going to be something like what we were doing with the first derivative test, right? We want to draw a real line with the x values on here, right? And then label our critical numbers, right? And do f prime. So we know that f prime is 0 at 0 and 3, right? And that gives us 3 parts, right? 0 and 3, these two critical points cuts the x-axis into 3 different parts. To the left of 0, between 0 and 3, and to the right of 3. And again, we're going to do the same thing like what we were doing in 3.3. We're going to pick checkpoints, right? Let's pick -1, 1, and 4, right? And usually, again, you want to pick nice numbers. Now, in this case, again, we only care about whether they are positive or negative, right? So f prime of x is the function for x squared times x minus 3. All right, and let's look at f of -1, f prime of -1. That's going to be a positive number multiplied by a negative number, which will be negative. Right? And f prime of 1, that's going to be a positive number multiplied by a negative number, which is still negative. Right? And last but not least, f prime of 4, that's going to be a positive number multiplied by a positive number, which is a positive number right here. Okay. Now, by looking at this, we can actually identify any of the local min or max. Right? So we do have a change of signs for f. Right? As negative to positive at x equal to 3. Right? So here we have a local min. Okay? And let's try to understand this in the original function f. Right? Negative means it's decreasing. Right? And between 0 and 3, that's decreasing as well. And at x equal to 4, to the right hand side of 3, f is going to be increasing. Right? So we do have some sort of behavior going downhill and then going up at x equal to 3. That's what makes it a local minimum, right? And again, this is based on the first derivative test. Okay. All right, and that's basically all the information we have for f prime. And that's it for step 3. Now let's move on to step 4. All right, so for step 4, we want to find the inflection point. Now let's do a quick review on inflection point. Inflection point is where the concavity changes sign, right? Inflection point is where f double prime changes sign, right? Or inflection point is where concavity changes. Okay, so we're going to do the same thing as we were doing, like in step 3. To find the inflection point, we want to find out what are some possible points of inflection, right? So we first need to find out where are some possible points that f double prime changes sign. And we know that if f double prime has to change sign, it has to cross 0 somewhere, right? So we're going to start by looking at where f double prime is 0. Right? Therefore, we have 12x squared minus 24x is equal to 0. And we're just going to solve this equation. Very simple, right? Factor out 12x. We get x minus 2 is equal to 0. And in this case, we get some possible point of inflection at x equal to 0 and 2. Right? So this is like looking for critical numbers, but these are not critical numbers. These are possible inflection point. Right? And we're going to do something like the first derivative test. We want to see whether f double prime changes sign at these 2 points. Right? So we have 0 and 2. Okay, and we know that f double prime is 0 at these points. Right? And again, we do the same thing. Right? We want to pick checkpoints. Right? Let's say -1, 1, and 3. And just like before, we only care about the sign. Right? So f double prime of x is 12x times x minus 2. Let's see. F double prime of -1 will be a negative number multiplied by a negative number, which is a positive number, right? Right here. And f double prime of 1 is going to be a positive number multiplied by a negative number, which is a negative number. F double prime of 3 is a positive number multiplied by a positive number, and that will be a positive number. Okay. All right, so we can see that they change signs at 0 and 2. That means these x equal to 0 and 2, these are a point of inflection. Now, unlike first derivative test, we don't need to worry about whether it changed from positive to negative or negative from negative to positive. As long as the sign changes, we can say that they are inflection point. Right? So let's also identify what the behavior here is at f. So to the left of 0, that's concave up because the second derivative is positive. Between 0 and 2, it's concave down. Right? Second derivative is negative. And after x equal to 2, to the right-hand side, we get concave up again because second derivative is positive. All right, so let's summarize this. We can say that x equal to 0 and 2 are inflection points. Okay, all right. And that's it for step 4, right? Finding inflection point and determine concavity, right? We have all the concavities right here, and then we know that 0 and 2 are our inflection points. All right, now the hard part is done. Step 5, we just want to summarize what we did in step 3 and 4. So let's start with the critical points, right? Critical points, we have x is equal to 0 and 3. All right, let me double check. Yeah, 0 and 3 are our critical points. And our point of inflections are x equal to 0 and 2. Right, inflection point at x equal to 0 and 2, right? And here we're going to put both f prime and f double prime on the same axis, right? So we have 0, 2, and 3. And let's say above the x-axis, let's do f prime, right? So f prime, let's see, let me go back and look at this graph. It's negative, negative, and after 3 is positive, right? So f prime will be all negatives here, and at 0, it's 0, and all negatives after 0, still negative at 2. All right, negative, 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 and at 3, it's 0. And to the right-hand side of 3, f prime will be positive, means it's going to be increasing. Okay. And let's look at below, f double prime. F double prime has 0 at 0 and 2, right? Point of inflection. Okay, and let's go back and check. Okay, so it's concave up, down, then up. Right, so it's going to be positive, 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 and then negative between 0 and 2. And after 0, it's going to be concave up, positive, all the way down. Okay. Now here we want to try to combine f prime and f double prime together, and let's see what that's going to look like. Before we actually get into that, I want to show you the different combination of shape of graph when you combine f prime and f double prime. Right? So here we have, draw a little table here. So we have f prime here and f double prime, positive, negative, positive, negative. All right, so when f prime is positive and f double prime is positive, that means it's going to be increasing and concave up, right? So it's going to be something like this, right? It has some shape like this. Let me do it again, right? Something like that. Okay, when f prime is negative and f double prime is positive, it's going to be decreasing, but concave up, right? Decreasing and concave up is going to look like this. Okay, it's decreasing, but it's concave up, like part of the cup. When f prime is positive and f double prime is negative, we are looking at increasing, concave down, right? So it will look like this, right? Increasing and concave down. And the last one, where both of them are negative, it's decreasing, concave down. right? That will look like this. Right. So you can see that it depends on the sign of f prime and f double prime. We're going to see different types of graph. Right? And what we're going to do is we're going to try to identify the graphs, which one fits in which interval. Okay, so let's see. Move this to the right hand side, maybe down a little bit. All right, so first, to the left of 0, f prime is negative and f double prime is positive, right? So to the left of 0, we have negative f prime, right? Decreasing and concave up. So it's going to look like this, decreasing and concave up. Between 0 and 2, it's decreasing and concave down. So it will look like that. Okay. Between 2 and 3, decreasing and concave up. That will look like this. Oops. Look like that. Okay. And the last part is increasing and concave up. So it will look like this. Okay. So that these 4 different parts tells us what the graph is going to look like, right? In break it down into 4 intervals, right? And the last step in step 6, we just want to find some points so that we can connect everything together. Okay. Step 6, plot key points, intercepts, critical points, inflection points, and sketch the curve by connecting the points with the shapes from the previous step. Okay, so here we are going to find the function value, the y value for the critical points and inflection point, as well as the x-intercept, right? X-intercept and y-intercept. So let's build a table, right? We have the x values, the y values, starting with the critical points, right? 0 and 3, and inflection points 0 and 2. Right? And let's label them. Right? So 0 and 3 are critical point. Right? And 0 and 2 are point of inflections. And also, when x is equal to 0, that's also our y-intercept. Right? And to find x-intercept, we just need to let y be equal to 0 and solve for x. Right? And that will be our x-intercept. Right, and all we need to do is fill out this table using the equation above, right? Y is equal to x to the 4th minus 4x cubed plus 10. That's our original function. Right, and take some time to evaluate them, right? So first, when x is 0, y is 10. When x is 3, let's see. When x is 3, y is going to be, let's see, 81 minus 108 plus 10. That's going to be negative 17. Okay. And when x is equal to 2, we have plug in 2, so that will be 16 minus 32 plus 10, that'll be negative 6. All right, and then we have our x-intercept, right? So we have to set that equal to 0 and solve. We're probably going to be a little bit annoying, right? So let's see. It's actually pretty hard to solve for this, but I'm just gonna use a computer or calculator to solve this. That's about 1.6. Okay. All right. So we have our 4 points, and let's try to graph them on the XY plane. All right. So first, we know that let's plot those points first, 0, 10, right? So let's do 5 and 10, right? 0, 10. We have 3, negative 16, right? So let's say 1, 2, 3, 4. 3 and negative 16, so negative 5, 10, 15, 20. 3 and negative 17, let's say it's about here. All right, and 2, negative 6, 2, negative 6, that's about here. 1.60, 1.60, that's the intercept, that's about here. Okay, so we only have these 4 points, okay? And next, we are going to connect these 4 points using these 4 shapes, right? So let me copy it down here. Okay, and then we can see a little better. We have to follow these shapes when we're graphing. All right, so to the left of 0, it's gonna go like that. Okay, so to the left of 0, so 0, 10, that's the y-intercept. So to the left, it's gonna go up, right? Decreasing and concave up. So it'll look like this, right? Something like that. Now 0, x equal to 0, that's a critical point, point of inflection, and y-intercept, right? So that means at x equal to 0, this point 0, 10, it will act as a horizontal tangent and the change of concavity. All right, so let's look at between 0 and 2. Between 0 and 2 is decreasing and concave down. Okay, so to 0 and 2, we're going to go from this point to 2 and negative 6 using this sort of curve. Okay, it's pretty hard to graph. Oh my gosh. Okay, there you go. Okay, and 2 at x equal to 2, that's a point of inflection. Right? So from here, it's going to change concavity between 2 and 3. It's decreasing concave up. Right, so we're going to start doing concave up. Oops. It's actually very hard to graph. Okay, well, that doesn't look like concave up. Let's say it's okay, something like that. And 2 to 3, it's decreasing concave up, right? Something like that. And then after x equal to 3, right, it's just going to increase in concave up, right? So we can do that. Something like that, and then it's going to go up like this. Okay, so just a rough behavior like that, right? Of course, in the middle, like between the specific points, it's very hard to get the correct points. But we do have 4 points as reference, right? The y-intercept, x-intercept, point of inflection, and critical points, right? So let's do a little label, right? 0 and 10. That's a critical number. That's a point of inflection, and that's also the y-intercept. Okay. At this point right here, about 1.6 and 0, that is the x-intercept. Okay. X equal to 2, 2 and negative 6. That's a point of inflection, right? Where its concavity changes from concave down to concave up. And this point right here, 3 and negative 17. That's a critical number, also a local min, right? It's not a point of inflection because the concavity does not change. It's always concave up, right? And that's basically it. This final graph is our answer, right? We graph a really rough sketch from all the information that we get from the first derivative and the second derivative. Right? Being able to get the behavior of the graphs and then find points and connect these points using the graphs we got from f prime and f double prime. Okay. Let's do another example. We want to graph this rational function x plus 1 quantity square over 1 plus x squared. And let's go ahead and just follow the steps. Step 1, we're identifying the domain. Now, even though this is a rational function, so basically we want to see what x values will make the equation undefined. In this case, denominator is 1 plus x squared, so it can never be 0. Therefore, everything is going to work in terms of the x value. So the domain will be all real numbers, negative infinity to positive infinity. All right. And there are no symmetries. And you can see that if we plug in, if we check if it's even or odd, it's not going to work out, right? It's neither even or odd. In this case, we do have asymptote. And for asymptotes on a rational function, right, in this case, the degree of the numerator is actually the same as the degree of the denominator. So the specifically the horizontal asymptote, it's going to be the equation y equal to leading coefficient of the numerator over the leading coefficient of the denominator. Right now, in this case, it's just 1 over 1, which is 1. Right, so we do have the horizontal asymptote y equals 1. Now, there is no vertical asymptote because we don't have anything that will give us 0 in the denominator. All right, and that's the first part. All right, the first part we have some information. The domain is all real numbers, and we do have a horizontal asymptote y equals 1. All right, 2, we need to find critical points, or y prime and y double prime. And let's do that actually. So y is x plus 1 quantity square over 1 plus x squared. All right, so to take the derivative, we will need the quotient rule. Okay, and here it is. Right, so 1 plus x squared, quantity squared in the denominator, and have a copy right here. 1 plus x squared, and then multiply by the derivative of the numerator, which will be 2 times x plus 1. Right, and the chain rule is 1, so we don't have to worry about that. Minus the numerator times the derivative of the denominator, which is just 2x. Okay, so let's clean this up a little bit. I'm gonna factor out 2 times x plus 1, right? And let's see what we have. We'll have the 1 plus x squared minus x times x plus 1 all over 1 plus x squared quantity squared. All right, let's clean this up a little bit. All right, so that's going to be 2 times x plus 1. And in the bracket, we're going to have the x squared canceled out. So we'll have, and the 1 is gone as well. So we have, let's see, 1 minus x, 1 minus x. One minus x, and all over 1 plus x squared quantity squared. All right, now if we set this equal to 0, right? Set y prime equal to 0, we get that x is equal to 1 and negative 1, right? We want the numerator to be 0, x plus 1 and 1 minus x. And when x is equal to 1 or negative 1, we get 0. That means these are our critical points. Critical points. And let's actually check those first before moving on to the second derivative. All right, and we can again draw the number line. Okay, so we have negative 1 and 1. And those are going to be, the f prime are going to be 0 at those values. All right, and let's check using a pick checkpoint. So we have a -2, 0, and 2. All right. So another way to do that is you can just plug into the derivative right here and see what we have. Okay. So plugging -2, we get a positive number. That's the 2. -2 plus 1, that's negative. 1 minus -2, that's positive, and then denominator is always positive, so that'll give us a negative number. Plug in 0, we get positive, positive, positive over positive, which is a positive number, right? And 2, I think that's going to be positive as well. Let's see. Oh no, it's actually negative. Positive, positive, and 1 minus 2, that'll be negative over a positive number, right? So that's going to be a positive number. All right, so let's try to understand it in terms of f, right? So to the left of 1, this is decreasing, and between -1 and 1, this is increasing, and to the right hand side of 1, this is decreasing. Of course, with -1 and 1 being the critical number, which is constant at those values. All right, let's move on to the second derivative. So the second derivative now, it's going to be a lot of trouble to find. Okay, but let's try it. Let's try it. Okay. I'm going to start by multiplying these two out. Okay, so we have y, y prime is this thing, right? Is equal to 2 times 1 plus x times 1 minus x over 1 plus x squared quantity squared. Now I'm actually going to multiply the numerator together like this. Multiply the 1 plus x and 1 minus x together. I'll get 2 times 1 minus x squared all over 1 plus x squared quantity squared. All right, and now let's find y double prime, right? Again, using the quotient rule on this part that we just multiplied out. Okay, so let's see. It's going to be 1 plus x squared quantity to the 4th power, right? Because we're taking the square of the denominator again. All right, copy it down. 1 plus x squared quantity squared times the derivative of the numerator, which is going to be -4x. Okay, minus 2 times 1 minus x squared, and then multiply by the derivative of the denominator, which is going to be 2 times 1 plus x squared, and multiply by the chain rule, which is 2x. Okay, so that's a lot of terms, right? A lot of terms. So definitely, if you don't understand what's happening here, you can feel free to pause the video and try this out on your own. Basically, we're just applying quotient rule on this quite confusing rational function. All right, next, let's clean this up a little bit. I'm gonna start by let's see what we can factor. Actually, let me clean up a little bit. So 1 plus x squared. Put the -4x in the front. So -4x times 1 plus x squared quantity squared. Let's multiply this out. 2, 4, 8. So minus 8x times 1 minus x squared times 1 plus x squared. All right, all over 1 plus x squared to the 4th. And the numerator, I'm going to factor out -4x times 1 plus x squared. And let's see what we have. So in the numerator, first part, we have 1 plus x squared left. And then a negative is gone, so plus 2. And the 1 plus x squared is gone, so 2 times 1 minus x squared. Like that. All right, and all over 1 plus x squared to the 3rd power, to the 4th power. Now you'll see that we actually can reduce 1 plus x squared with one of the 1 plus x squared in the denominator. So leaving us to the power of 3 in the denominator, and in the numerator we'll have negative 4x. Multiply this out, that will give you a 3, and then x squared minus 2x squared. That'll be minus x squared over 1 plus x squared to the third power. Now that's the second derivative, right? And we're going to set this equal to 0, right? In order for us to find a possible point of inflections, right? So when you set that equal to 0, all possible x values are x is equal to 0, right? From the negative 4x, or x is equal to a plus minus square root of 3, which is coming from the 3 minus x squared. All right. Okay, so let's see. That's 3 possible points of inflection. And let's do that. Again, draw the real line. All right, so we have 0, negative we're at 3, positive we're at 3, right? And we know f double prime is 0 at these points. Okay, and all we need to do is pick some checkpoints. Let's do negative 2, negative 1, 1, and 2. So square root of 3 is about 1 point something, right? So we know it's between 1 and 2, so we can pick those checkpoints. All right. Now I'm actually going to do this quite fast. So that will be positive, negative over, it's going to be a positive number. Right? So that's negative, concave down. Plug in negative 1, that's be positive, positive, positive. So concave up. Plug in 1, that's negative, positive, positive. So concave down. Plug in 2, we get negative, negative over positive, which is positive, right? So concave, concave up. Right? So let's summarize this. So to the left of negative square root of 3, it's CC down. Between negative rad 3 and 0, it's CC up. And between 0 and positive rad 3 is CC down, concave down. And then to the right-hand side of radical 3, it's CC up. Okay, so you can see that at every value that we found, 0, plus, minus, radical 3, all of them have changed concavity, right? CC down to up, so that's a point of inflection. Concave up to concave down at 0, that's a point of inflection. And then from concave down to concave up at x equal to radical 3, that's another point of inflection. Right? All right, so we do get a lot of values to work with here. And let's see. And again, we're going to do the same thing by putting the first derivative and the second derivative together to see what we have, right? What sort of behavior we have. Okay? All right, let's do that. Okay, so let's identify the critical numbers first, 1 and negative 1. Right, let's say 1 and negative 1. All right, those are our critical numbers. F prime is 0, 0. And then we want to see what happens in between, right? So it's decreasing, negative, positive, and positive. All right. Oh, that was supposed to be decreasing right here. Right, that should be negative, which is decreasing. Okay, so decreasing, increasing, and decreasing. That means F prime is negative, positive, and then negative. All right, now let's look at F double prime. Put it below. We have 0.0, Negative rad3 and positive rad3. Right? So negative rad3 is to the left of -1, and positive rad3 is to the right of 1. Okay, so what do we have? We have negative, positive, negative, positive. All right, so it's going to be negative, 0, positive, 0, negative, 0, and then positive to the right. Okay, so let's see how many intervals do we have, right? So I'm going to try to label this. We have 1, 2, 3, 4, 5, and 6, right? So in each interval, we're going to look at what type of graph we have. All right, so to the left of negative rad3, it's decreasing and it's concave down, right? So we have something like this, right? Between negative rad3 and -1, it's decreasing concave up, right? So it'll be look like this. Between -1 and 0, it's increasing and concave up, right? So something like that. Curve a little more, right? Something like that. Between 0 and 1, increasing and concave down. Increasing and concave down, that will look like this. Okay. And between 1 and radical 3, decreasing and concave down. Okay. And to the right of square root of 3, it's decreasing and concave up. So it'll look like that. Okay. So we have these 6 intervals with different f prime and different f double prime, and that gives us the basic information of what we have. Okay. All right, and next, let's write down a table of all the values we need. Okay, so x, first we have the intercept, right, which is going to be 0, 0. Oh no, sorry, x equal to 0, and then we are going to have the critical numbers, 1 and -1, as well as the point of inflection, 0, radical 3, and negative radical 3. Right. And the original function, let's do a quick review. The original function is y equals x plus 1, quantity square, over 1 plus x squared. Right, so when x is 0, I get 1 over 1, which is 1. And when x is 1, we get 2. When x is -1, we get 0. Okay. Let's see. And when x is 0, we get 1. So we actually covered that already. Okay, that's 1 again, repeating. When x is radical 3, now this is where you might need a calculator to help you, but it's approximately 1.9. And when x is negative radical 3, it's about 0.13. All right, let's try to plot these points first, and then we will come up with some other information. Okay, and notice that that's our x-intercept. Oh, sorry, that's our y-intercept, and that's our x-intercept. Okay, and also these two are critical points, critical numbers. And to be a little more specific, if we go up and look at the first derivative test, we can see that it's decreasing to -1 and increasing after -1. So we actually have a local min at -1. And at 2, it's going to be increasing to 1 and decreasing after 1. So we actually have a local max at 1, right? So let's write it down as well. So x -1, that's local min. And when x is 1, that's local max. Okay, and then of course the last 3 points, these are your point of inflections where the concavity changes. Okay, so let's plot these points first. All right, Let's see, 0, 1. Okay, let's see. 0, 1, say right here, 1, and then negative 1, 0. Okay, negative 1, 0, 1, 2. And then radical 3, 1.9. The radical 3 is somewhere between 1 and 2, pretty close to 2. Right? Let's see. 1.9, it's about here. And then negative rad 3 and 1.3. So that will be somewhere about here. Okay. All right. So let's try to connect these 5 points together using the information above right here. Okay, so to the left of negative 3, we get something like that, right? It's concave down and decreasing. Okay. So let's say something like that. Okay, and then between radical 3 and negative 1, it's going to be decreasing and concave up. And negative radical 3, that's a point of inflection, right? So we want to change the concavity here. And notice that we actually have to go to negative 1 right here. So let me redo this one. Let me see if I can do it a little better. Right, something like that. Okay. All right. Between negative 1 and 0, increasing and concave up. Okay. So look like that. Okay, pretty good. And between 0 and 1, it's going to be increasing and concave down. And 0, x equal to 0, that's a point of inflection. So change concavity from concave up to concave down. Okay, something like that. And then between 1 and 2, 1 and radical 3, it's decreasing concave down. Okay, so it's still concave down. Very hard to draw. Let me redo this part. Okay, there you go. All right, and to the right-hand side of radical 3, it's going to be decreasing and concave up. All right, so it's a little hard to draw. Something like that. Okay, something like that. Decreasing and concave up. All right, now even though this might not be the best picture, right, but of course we are just graphing by hand, and we do see some the properties that we have from the first derivative and second derivative test, right? And then we do have the horizontal asymptote of 1, right? Y equal to 1. And you can see the end behavior as x goes to negative infinity and positive infinity. The line is actually getting close to 1, right? So maybe we should fix that this part to the left hand side a little bit, making it so that it goes to 1 like that. Okay? So we actually did a good job on the right hand side. Now let me show you a better picture, right? That's graphed by computer. All right, so here it is, right? That's a graph of the function by a computer. So you can see some sort of resemblance. Of course, we're not as accurate as, well, what the computer has, but I think it's a pretty good, I can see some sort of resemblance between these two graphs, but of course we are humans, right? And there is only a certain amount of accuracy we can get when we graph by hand. All right, yeah, but that's basically it for graphing a rational function using the first derivative and second derivative. All right, and that's it for this section. Thank you guys very much, and I'll see you next time.